let's try one more example. So here we're going to do the integral from 0 to 4 of the function x divided by square root 2x plus 1. And we're integrating with respect to x. All right, so first, before we get to any of the substitution rule, let's rewrite this function. We know with root signs, a lot of times we want to rewrite them with as a power function. So let's rewrite this function. So we'll put our x first, and then we're going to have 2x plus 1. And inside the parentheses here, we want to get rid of this root sign, so it's going to be raised to the power 1/2. And it's in the denominator right now. Let's get rid of the fraction and use a negative exponent instead. So we're rewriting our function here as x times 2x plus 1 raised to the negative 1/2. And then we have our differential dx. All right, so we're going to worry about doing this definite integral. And rewriting it like this, we see a nice set of parentheses, we see a power function here, and then we see something kind of complicated inside the parentheses. So for substitution rule, our first step is to make a choice for u. And so we're looking for an inner function, essentially. We're looking for what's inside the parentheses. That's going to be our choice for u. So we're going to let u equal 2x plus 1. All right, so that's the hard part. Just looking at this function and being able to identify or choose u. All right, so next we want to calculate du. So we differentiate. I'll leave a little more space there. We're going to differentiate. So derivative of 2x plus 1 is 2. And then we multiply that by dx. All right, so we have our two little ingredients here for our function. And so we know part of the substitution rule process involves converting all of these x terms that we see into u terms. So by design, this 2x plus 1, that's going to become u. So we'll have u raised to the negative 1/2 here. We also have this dx. So let's look at what we have. Let's compare what we have with our differentials. So we have a dx here. Over here we do have a dx, so that's good. But then we have this extra constant of 2. But we know what to do with extra constants. We can solve this equation for dx, and that's what we're going to do. So we're going to solve this for what we have, dx. So divide both sides by 2, we get dx is equal to 1/2 times du. So this differential dx here at the end, we're going to be able to switch that over to 1/2 times du. So the question then is, what are we going to do about this x right here? That's kind of the only thing remaining in our function that we haven't switched over. The 2x plus 1 became u. The dx became 1/2 times du. What are we going to do about this x? Well, sometimes if you have x terms that are still there, then you go to your choice for u and you try to solve for x. So we're going to solve this equation for x. So subtract 1 from both sides, and then divide by 2. And so that'll give us x is equal to 1/2 times u minus 1. So subtract 1 from both sides and then divide by 2, and that gives us what x is. X is equal to 1/2 times u minus 1. And that is going to go right there for our x. All right, so let's start plugging all of this in. So our integral is going to be, well, we'll worry about the limits of integration in a second. Let's just worry about our function for now. So this x here is going to become 1/2 times u minus 1. The 2x plus 1 is going to become u, so we're going to have u raised to the negative 1/2. And then our differential here gets converted, and we'll have a 1/2 times du. All right, so there's our integral. We've switched over all the parts of our function here. And now we want to kind of decide on what are we going to do with our limits of integration. So you have two options. We can either convert them now, or we can leave them as is and then convert our antiderivative back to x later. So method 1 or method 2. Doesn't matter which one. It's roughly the same amount of work. It really comes down to which way you like to do it. Let's use method 1 here. But method 2 also would work. So I'm going to leave the limits of integration as x equals 0 and x equals 4. And I'm really emphasizing the fact that I'm not doing anything here with our limits of integration. I'm leaving them as 0 and 4. And so to really emphasize that, I'm writing them as x equals 0 and x equals 4, just to help remind myself that since I'm doing it this way, I need to convert my antiderivative back to x. So right now, I have this function. It's all in terms of u. I'm going to get an antiderivative that's in terms of u, and then I just want to make sure I convert back. You know, if we were going to do method 2, well then I would just convert over these limits of integration right now. So it just depends when you want to do it. Really, it's the same amount of work either way. You know, so our upper limit, if we wanted to do the other option, take x equals 4, plug it into your equation for u, you'd get 2 times 4 plus 1, which is 9. So another way is you would rewrite this with u equal to 9. And then same thing for the lower limit. Take x equals 0, plug it in, you'd get 2 times 0 plus 1, or u is equal to 1 would be your lower limit. So either way, however you want to do it, just be consistent. As long as you know, if you're converting over these limits of, or if you're leaving these limits of integration in terms of x, just make sure we convert our antiderivative back. All right. So this is good. Now we want to, before we actually get our antiderivative, we want to multiply all of this out. So we have some constant multiples here. We have some u terms. So really the fact that this is a product of two u terms means we need to multiply this out. So we're going to take this u to the negative 1/2. We're going to multiply it to the u right here. And we're going to multiply it to this one term right here. And then while we're at it, I have a 1/2 times 1/2. Well, let's multiply out the u's first. So the u raised to the negative 1/2 times this u term. We add the exponents. It gives us u to the 1/2. And then I'm going to have minus u raised to the negative 1/2 when I multiply it with this negative 1. And we're going to have a 1/2 times 1/2, so that'll be a 1/4. And while we're at it, let's multiply that out as well. So I probably could have done that in the last step, but there we go. All right, so now let's integrate each of these individual terms just using power rule. So the first term here, I have a 1/4, so that's going to stay in front. Let's integrate this u raised to the 1/2. So our variable is u. We add 1 to the exponent, takes us up to 3/2. Take that exponent, flip it, put it in front. So we have 1/4 times 2/3 times u to the 3/2. Then we go to our next term. We have a minus 1/4. Let's add 1 to the exponent here. So it takes us up to positive 1/2. Take that new exponent, flip it, put it in front of the u. So 2 over 1 goes in front. And this is our antiderivative. And we're going to evaluate from x equals 0 to x equals 4. Simplify this thing down a little bit. So some of the 2's and 4's we can clean up a little. And we're also going to convert back to x. So instead of u raised to the 3/2, or instead of u raised to the positive 1/2, we're going to convert that back to 2x plus 1. So 1/4 times 2/3 is 1/6. 1/4 times 2 is 1/2. So this first piece here is, instead of u raised to the 3/2, we're going to have 2x plus 1 raised to the 3/2. And then for this next piece, we're going to have 1/2. And then instead of u, it'll be 2x plus 1 raised to the 1/2 power. And we'll evaluate this from x equals 0 to x equals 1, or x equals 4. All right. So now we have our antiderivative. Our antiderivative is back all in terms of x. So now we're ready to start evaluating. So take the top number, plug it in. We get 1/6. And when we plug 4 into this piece, we get 9 raised to the 3/2. Then we have minus 1/2. Plug 4 into this piece, we get 9 raised to the positive 1/2. That's what we get when we plug 4 in. Then we plug 0 in. And when we plug 0 into this piece here, we're going to have 1/6 times 1 raised to the 3/2. Plug 0 in here, we're going to have minus 1/2 times 1 raised to the 1/2 power. And there we go. We have our answer. Now we could actually simplify this down a little bit, but that's fine. There's our nice value for our definite integral. Yeah, but like I said, we could actually simplify this down, but it's not absolutely necessary. You know, so we could do, what's the square root of 9? 3. So this would be 3/2. What's the square root of 9 here? 3. And then what's 3 cubed? 27. So this would be 27/6. So there is some simplifying we could do, but we'll stop there with this one. So this was going through a substitution rule where we left our limits of integration all in terms of x. So it's perfectly fine. Just go through substitution like you normally would, and then once you have your antiderivative back in terms of x, that's when you plug in. So that's method 1. If we wanted to try this one using method 2, all of this work, just about all of this work, would be exactly the same. So all of the difficult work here of choosing u and calculating du and all plugging in this function, all of that would be the same. The only difference is right here. So for method 2, we would have found our upper limit was u equal to 9, and our lower limit was u equal to 1. So that might have been the only, that would have been the only difference. And then really, we wouldn't have had to convert our antiderivative back to x. We would have gotten to this step right here, and our limits of integration would have been 1 and 9, and then we would have just plugged in and gotten the same answer. So, just decide which method you want to use. We kind of use the first method of just leaving everything in terms of x, but if you want to convert the limits of integration, do that. So whichever way you like, that's the method you should try. All right, so in the next lesson, we're going to kind of look more into, we'll start talking more about what these definite integrals actually represent. And so we're going to see that they're actually related in some way to area calculations. So we're going to start investigating that next. So we'll see you there.